Okay, how's everyone feeling?
Totally awesome, sir!
So we're going to do another inelastic collision problem, and we're going to use angular momentum to solve this problem. But this time, it's kind of bizarre because this red wad of clay right here is going to be going in a straight line, and you might think it doesn't have angular momentum. It's not rotating, but yet an object going in a straight line does have angular momentum. And when that wad of clay sticks to the end of this board, that's hinged at the one end, an inelastic collision occurs, and then the board and the clay start to pivot about that pivot point down here. So conservation of angular momentum. The angular momentum of the clay board plus the angular momentum, oh, not the clay board, the clay ball, plus the angular momentum of the board before the clay hits it is going to equal the angular momentum of the clay stuck to the board, rotating about the pivot point. So let's start off by calculating the angular momentum of the clay ball. This is the tricky one. This is the bizarre one. Because even though it's going in a straight line, it still has angular momentum. And if I jump up to this slide right here, this angular momentum, I times omega, translates into m times r times v as the ball goes past this point P right here. The moment of inertia is mr squared. The omega is the tangential velocity over the radius. Notice one of the r's cancels out. And you're left with mrv. So this is a weird type of thing because this ball going in a straight line like this would still have angular momentum about this point here. So I come back over here, and it's just going to be the mass of that ball times the perpendicular radius, in this case, that's the width of this board right here, times the incoming tangential velocity. So for that wad of clay coming in, it's going to be 1.5 kilograms times our perpendicular is going to be 2 meters times that incoming velocity of 3 meters per second. Now, this board right here that's hinged on that side right there, it's not rotating prior to the clay hitting it. Since it's not rotating, if I said, oh, that's going to be equal to I times omega, omega here is going to be 0 because it's not rotating yet before the clay hits it. So this term's just going to drop out because the board's not rotating yet. It doesn't have angular momentum yet about this point prior to the clay hitting it. So that term drops out. Now that's going to be equal to the angular momentum of the clay stuck to the board as it now swings over this way. Woo! And our mission is to calculate how fast it swings open after the clay hits the door. Now this is going to be equal to I times omega of the clay board combination. But this is complicated, so I'm going to scroll this down a little bit lower here. This I right here, it's the I of the clay ball plus the I of the board. The I of the clay ball, that's just the mass of the clay times that perpendicular r squared. The I for the board, that's not one you're supposed to have memorized. You would get that from a chart in the textbook. The I for the board, swinging around like that, that would be given to you. It's this formula right here. If you have a board swinging around a point right here, the moment of inertia, the amount of rotational sluggishness about that point, is calculated by this formula right here. If you take AP Physics C next year, you'll actually derive that formula using calculus. So we're going to use that formula way down here. And this is going to be 1/3 the mass of the board times the length of the board squared. That all times the final angular velocity as it swings open. So if I put in the values here, the mass of the clay is 5 kilograms. Oh no, 1.5? Yeah, 1.5. Scratch that. 1.5 kilograms times r perpendicular, and how long was that board? 2 meters, and that sucker gets squared plus 1/3 times, again, this is going to be the mass of the door. The mass of the door, what was it, 3 kilograms? Times the length of the door squared. How much is that? 2 meters squared. And then this is all in brackets. And what do I have to multiply all that by? Omega F. And if you simplify all that out and crunch that all out, you could solve for the one unknown. And did anyone actually crunch all that out and get an answer? What'd you get? So that's a lot more difficult than dropping the disc on the spinning disc problem. Because who knew a wad of clay going in a straight line has angular momentum? I know I certainly didn't at first. Yes. No, because the L is the length of the door. If you come back. If you have a swinging length of board and you're swinging it around its endpoint right there, the length is...
Yeah, I thought that meant L as in...
No. That's a great point. Thank you. This L right here is the length of the board. Excellent point, because that is very confusing. Thank you. Not the angular momentum.
I don't see how they got 0.75. I got 0.9.
Yeah,
I got 0.9
too.
So 0.9.
It's
It's
0.9.
on the other side. 1.5 times 2 times 2.
And if you put it back into the equation, you get like it to work if you have 9, 10 as the second. Then I think you would
Okay, so correction on the answer. This answer here, the final angular velocity comes out to be 0.90 radians per second. All this was still correct right here. It was just a big calculation.